Okay, here we have a question where we're looking at the decomposition of Tylenol in the body. I think we've all taken Tylenol before. Great for a headache. And in the prompt, they tell us that the half-life for Tylenol in the body is 3 hours. So if you take 10 milligrams, 3 hours later there will only be 5 milligrams left active in your body. Okay. So then it asks us to find the rate constant for this first order removal. And so this first order component of the problem is really important because it tells us we can use this half-life equation. Where the half-life equation is different between first and second order problems, so you want to make sure you can identify the right equation. So here we can go ahead and say 3 hours is going to be equal to 0.693, which is the same as the natural log of 2, divided by k. Half-life and k go hand in hand together, so if you know one, you can always find the other one. And when we plug this in, we get that k is equal to 0.231 per hour. So now they ask us what the concentration of Tylenol is in the body after 8 hours if a student starts with 32 micrograms per mil. And so when they gave us an initial concentration and time and ask us for a final concentration, we'll use our first order integrated rate law expression, which you can find on the data sheet. And it's the natural log of concentration at some time is equal to the natural log of our initial concentration minus KT. So we can organize our information here. So A naught is at 32 micrograms per mil. K is what we found from the last problem. And our time is 8 hours. So we can plug these values into the equation and solve for AT. We end up with an expression like this. We can then go on to simplify the expression and find that the natural log of AT is equal to 1.62. So this isn't our final answer because we have the natural log of AT. So we'll have to do both sides are exponential, and this will tell us that our final concentration after the 8 hours is equal to about 5.1 micrograms per mil. Okay, so then they ask us instead, how long will we have to wait for the concentration to be 2 micrograms per mil? So we can use the same kind of setup where we have our initial concentration, 32 micrograms per mil. Except now we know what our AT is. Our K is still the same because we're at the same temperature. And we want to figure out what T is. So we can put all that information again into the same equation. We have the natural log of 2 micrograms per mil is equal to the natural log of 32 micrograms per mil minus K times T. Okay, so then we can rearrange our expression to solve for T. We find that T is equal to 12 hours. Okay, and what's interesting about this is that 12 hours is the same as 4 half-lives, because our half-life was 3 hours. So we can kind of do a check. if we start with the 32 micrograms, let me move what I'm writing. If we start with 32 micrograms per mil, okay, let's just say we start with 32. And to go to 16, then is 1 half-life. And then to go from 16 down to 8 would be another T1 half. And then to go from 8 to 4. To go from 8 to 4 would be a third T1 half. And then to go from 4 micrograms per mil to 2 micrograms per mil would be our fourth T1 half. And so that matches up with what we'd solved. And we can use this logic because we know that for a first order reaction, T1 half is constant. Whereas if this were a second order reaction, if our first T1 half was 3 hours, then our second half-life would take 6 hours, the third would take 12 hours, so on and so forth. It would keep doubling.